Hi, today we're going to be talking about chapter 13, section 1. Let's go ahead and go over the introduction. The path of objects moving through space, like the planes pictured here, can be described by vector functions. In section 13.1, we will see how to use these vector functions to determine whether or not two such objects will collide. Okay. The functions that we have been using so far have been real value functions. We now study functions whose values are vectors because such functions are needed to describe curves and surfaces in space. We will also use vector value functions to describe the motion of objects through space. In particular, we will use them to derive Kepler's law of planetary motion. Okay, so let's go ahead and get started with this section 13.1. And let's go ahead and talk about vector functions and space curves. A vector value function is a function whose domain is a set of real numbers and whose range is a set of vectors, okay? So here's the vector function. We're going to use R of t, and you should know this notation for vector function, but we do not only use this notation, we can also use this other notation. We use t to denote the independent variable because it represents time in most applications of vector functions. Okay, let's go ahead and go over example number 1. If we have the vector function equal to t to the third ln of 3 minus t square root of t, can you find the components, only the components of the function? Find the components of the function and determine the domain of the vector function. Okay, the first thing that we want to do is we want to find the components first of all. Well, the components are each one individually. So this one happens to be f of t, this one happens to be g of t, this one happens to be h of t. And we have 3 components, f of t, g of t, h of t. Okay, let's go ahead and write that down now with words. Okay, so then we have the components are f of t equals 2 to the third power, g of t equals ln 3 minus t, and the last component, h of t, it's equal to the square root of t. Those are the components of your vector function. Now, in order for us to be able to find the next part says to decide the domain of the vector function. Okay, well, in order for us to decide the domain, I gotta consider each component individually. What's the domain for a polynomial? I hope you guys are thinking all real numbers for this polynomial here. What's the domain for g of t? We have ln, which is a log, your argument, which is 3 minus t. 3 minus t cannot be a negative number. So this has to be strictly positive. Strictly positive. And okay, so now what we're going to do is we're going to solve for t. So I can add the t to the right side. So this will be t is greater than t. I'm going to rearrange the order. T is less than 3. And that will be the domain for g of t. I need to find the domain for h of t. Now the domain for h of t we have a radical, and we know that inside the radical, we cannot have any negative values either. So inside here, we cannot have no negative values. And so for that reason, all of the values that I put in here, it has to be strictly greater than or equal to 0. Okay, so now you don't have to put it on a number line, but you can. It really does help some students. Okay, I am looking for the overlap between all 3 of the components together. The first one gives me all real numbers, which is great. It takes every number. But the second component, ln, only takes values of t that are less than 3. So let's say 0, this is 1, this is 2, this is 3, this is -1, then this is -2, not drawn to scale. Okay, but t is less than 3. So I'm going to take any number to the left of it. But then I have the other one, which is the last component, h of t, and that one says I take any component that is greater than or equal to 0. So greater than or equal to will be this way, yes? Well, the overlap of all of the 3 components happening here. And so then the domain will be that one. Domain of the R vector function is from 0 to 3, including 0, but not 3. That's the way you're going to do it for each one of these ones. So if they ask you for those things, then this would be the way to do it. You're going to separate it into the components. You're going to separate them. You're going to consider each of the components domain. Then you're going to put them all together into one. And that will be the domain for your vector function. Okay, let me go ahead and move on now. Now, we do know that limits exist. Actually, this will follow to say that our vector function can also have a limit. So if we have a vector function, we can also take the limit of that vector function. And what we can do is, if we take the limit of our vector function, we can also take the limit of each component of our vector function, provided that the limit of the component functions exist. Let's go ahead and do an example for the limit one. Okay. So then what I am going to do right here is we are going to take the limit. So we're going to multiply everything by the limit. So then this will be the limit as t goes to 0 for the vector function. This will be equal to the limit as t goes to 0 for the first component, 3 plus t to the 5th power I plus the limit as t goes to 0 e to the negative t j plus the limit as t goes to 0 for sine t over t with the k component. Well, the limit as t goes to 0 for this polynomial, if I substitute the value directly into the limit, then the limit will just be 3, okay? 3i. If I substitute the value of t is equal to 0 for this function e to the negative t, that will give me a 1. Now, the limit as t approaches 0 for sine of t over t is always equal to 1. And that would give me k component. And so in this case, this will be your vector. This will be a vector of your limit function. So we can write it down in this form, or remember that you can also express it in this other form. And so both answers will be correct. That's it. That's the way we're going to be taking the limits of vector functions. Let me go ahead and move on to space curves. There is a close connection between continuous vector functions and space curves. Suppose that f, g, and h are continuous real value functions on an interval L. Then the set C of all points x, y, z in space where x represents f of t, y represents g of t, and z represents h of t, and t varies throughout the interval L, is called a space curve, okay? C is traced out by the tip of the moving vector r of t. Okay, we have a quick picture. We have a space curve. We can see the space curve. It's kind of highlighted in red, and it's making some sort of a motion, and it's also making some sort of traces. We can also see the vector function at a certain point on the space curve. And so that would be our C. Okay, this is what we're going to be doing, okay? We are going to be given, they're going to give us a space curve. I'm sorry, they can either give us a curve in the XY plane, or they can give us a surface in XYZ. If that's the case, we're going to use one or more components to get a curve or a surface. We're going to try to get rid of t if it's possible. Second, we're going to make an observation. Two components. If they give us two components, when I say two components, I'm talking about, let's just say r of t is just equal to, let's just say, 3t and 2t, for example. That's two components. If I am saying three components, then I am saying this 3, 2t, let's just say t squared. That's three components. We'll have a two component, we're going to sketch a plane. Three components, we're going to sketch a surface. Then we're going to use the values of t in order for us to generate an orientation on the curve. Okay, so this is basically what's going to happen. This is just a quick example. Suppose I have a cylinder. We have the shape already. We have the equation of the cylinder already. So this will be a three component. We have a cylinder. The way I have drawn it, it seems like it will be on your z-axis. So we can, label it, something like this if you want to. So we have a cylinder right here, but I want some sort of an orientation. So I want to know if my orientation starts right here or if it starts where. It has to start someplace on the cylinder, okay? So what if it makes a turn and it goes to here and then from here? What if it goes from here and, where does it go? Is it going like this and then it keeps on going up? And so those are the little things that I am going to be looking for. And these points are going to have to be on the cylinder. Okay. Okay. So let's go ahead and get started with our first example. It says, describes the curve defined by the vector function r of t is equal to 1 plus t, 2 minus t, 3 minus 2t, and t is from negative infinity to infinity. So all real numbers. Okay, let's go ahead and discuss the components. So in this case, my components are x equals 1 plus t, y equals 2 minus t. And z equals 3 minus 2t. And I can see that none of them have been raised to no power. So the t's are a single t, there's no powers, and I can clearly see that this is an equation of a line. This is describing of a line. Okay, so I gotta know that. Okay, now I have 3 components. Okay, we have 3 components. Okay, so notice that I can use this. I have 3 components, so then that will give me a surface. Okay, I have a surface. Okay, so now since I have that, I am ready to draw my my z, my x, and my y. Okay, I have certain things in here. So things that I can make an observation very quickly. I can see that since this is an equation of a line, I have a point. One point on the line will be the point if t is equal to 0. I get the point 1, 2, and 3. Another thing that I know is that I have a vector, and my vector will be 1, -1, and -2. And the vectors are coming from here. So the leading coefficient for the first one is 1. The leading coefficient for the second one is -1. And the leading coefficient for the last one is -2. So that ones are my vector components. Okay, so that's what I have. That's what I have so far. All right, so let me see. Not possible for me to be able to, because step number 1 says try to get rid of t if you can. Well, I guess you can. I guess you can do that. We can get rid of the t. We can solve x equals 1 plus t. It will be x minus 1 is equal to t. And then I can plug that into my second equation. Y will be equal to 2 minus x minus 1. And so then that will give me 2 minus x plus 1. So y will be 1 minus x. Okay, and so this would be a line. Okay, this is an equation of a line. I can actually use those 2 components to draw it. And so I can do that if I want to. I can select a few points and draw it. So we can do that. So for example, if x is 0, y will be 1. And then if x is 1, y will be 0. So you can generate a few points if you want to. However, for this particular problem, I did not do it that way, okay? Because I probably forgot to do it that way, but this will be one way. But here's the other way that if you kind of forget to do that, you can also do it this other way. So I'm going to go directly to select a few points, okay? So I'm going to say let t be equal to 0. If t is equal to 0, and I plug it in here, of course, we're going to get this ordered pair. So my point would be 1, comma 2, comma 3. And then let t be equal to 2. And if I plug it in the same equations, t equals 2, then x will be 3, y will be 0, and z will be -1. So I have two order triples. And so I can graph them. Okay, so try to graph them. So we have, I don't think I want to label that one. Okay, so I'm still going to use maybe the yellow color. So X will be 1, Y will be 2, and Z will be 3. So like about here, it's not exact. Then X will be 3. Y will be 0, and then Z will be -1. So let's just say like about here. I'm going to connect the dots. Once again, my line can be a little off. Oh my gosh, I can't draw my line. Okay, this is the line that I get when I draw it. It's not a perfect. Now you can see that my line does not contain any arrows because I don't have any arrows, okay, yet. Okay, so the point is this one, 1, comma, 2, comma, 3, and the other point that I have is over here, 3, 0, -1. Okay, now what we care about is the orientation. I can still select the same values, t equals 0, but I'm going to put it into the vector function. Okay, so when I put it into the vector function, I hope you guys can see that you should be able to get the same order pair, but it's no longer an order pair, it will be a vector. Because if t is 0, this would give me a 1, this would give me a 2, this would give me a 3, okay? So I have a vector, okay? And then if t equals 2, and I put it into the vector function, then I should get 3, 0, -1. And so now I can clearly see that it will be going in this direction, yes? And so then that will be the direction that it's going to take for this line. Okay, let me go ahead and move on to example number 4. So for example number 4, we're going to be sketching another curve. Sketch the curve whose vector equation is RT is equal to the square root of ti plus 4 minus tj, and t is greater than or equal to 0. And so then I'm going to do the same thing as before. I'm going to check the components. And so I can clearly see the components. X equals to the square root of t. Y equals to 4 minus t. I have 2 components only. Since I only have 2 components, then we're going to draw the rectangular coordinate system. X and Y. Okay, now, I have 2 components. That's what I'm going to do. I don't know what the graph is. Let's go ahead and go back to step number 1. It says go ahead and observe the components. Is it possible to solve for one of the letters? For get rid of solve for t. So right here we're going to square both sides. So then this will give me x squared. It's equal to t. I'm going to come back and I'm going to plug it in here. So then that is going to give me y equals 4 minus x squared. And this is actually something good because I know what that is. That is describing a parabola facing downward. shifted up by 4 units, okay? And so I really don't need anything else. 1, 2, 3, and 4. And so I know that I have a point right here. The other thing that I know is I have some intercepts. For example, the intercepts would be if we let x be equal to 2, then y will be 0. If x equals -2, y will also be equal to 0. So then I have 2x intercepts. I have one right here and one right here. And so I know that this is a parabola that opens downward. However, I gotta pay attention to this part. T is greater than or equal to 0. Since t is greater than or equal to 0, that's going to affect it. It's going to affect it over here as well. And so I know that I can now have negative values for t. And so then in reality, I don't have this piece. Okay, I only have that part of the parabola. Okay, only half of the parabola. Now I need to know the orientation. So let's go ahead and discuss the orientation now. And so for the orientation, I'm going to let t be equal to 0. If t is equal to 0, I'm going to put it in here. And so then that will give me, when I put it in here, so we're going to be putting it in here or here. So if I put it in there, I lose the i's and I only get a 4j. Zero and 4. Let t be equal to 4. When I put it in here, the reason why I selected a 4 is because this can go away, yeah? And so then I get the square root of 4i only. I don't have the j anymore. The j is gone. So this will give me 2i, or this will give me 2 comma 0. And that's enough for me to be able to know, yeah, because 0 and 4 is here. And then 2 and 0 is also here. And so we already know that it's coming this way. By the way, those points happen to be on the curve. Okay, so then that's it for example number 4. Are you ready to try one on your own? Well, I don't know you're ready to try one on your own. I'm going to give you another example right here. So example number 5. You can pause the video and you can try this one on your own, but we'll see. Okay, so then we have another vector function, components. Go ahead and start the same way for all of them. And so x equals t, y equals t squared, z equals t to the third power. We have 3 different components. 3 components mean we have a surface, and so we are going to be using the XYZ plane. All right, remember 3 components, we can use at least one or more, not all of them. It's not necessary for us to use all of the components. Okay, we can clearly see right here that this one has been solved for t already, so I can plug it into this one. And so then I get y equals x squared. I don't have to use a z, by the way. I don't have to. Remember, 2 components will be enough. Okay, so now this represents a parabola, okay, in two dimensions. Okay, in two dimensions, this represents a parabola, but this one has two variables. Remember that if we have two variables, then it describes a cylinder. So we have a cylinder. The missing variable is z, so it will be a cylinder along the z-axis. With traces on the xy plane. If we let y be equal to 0, then I get x squared is equal to 0, which means x is equal to 0. If I let y be equal to 1, then x squared will be equal to 1, so x will be equal to plus minus 1. If y equals 4, I get x squared will be equal to 4, so x will be equal to plus minus 2. I'm only going to be using right now the xy. No z's right now. Z can be any number, any value of z, because z happens to be free, okay? Okay, so then the order pair that I will have is 0, 0. And then remember, z is like free. But I want z to be 0, so then z can be 0. Or I can have 0, 0, and z can be 1, you know. 0, 0, and z can be 5. So we actually have a height, okay? Okay, so I will show you in a moment. Then the other one will also have an order pair like this would be like a 1 and a 1, and then z is free, or negative 1 and 1, and we have a z is free. This is the z. Okay, so then I have 1 and 1. X is 1. Y is 1. And I'm going to make my z 0. Okay, so if that was the case, then my point will be somewhere in here. And I can do x is negative 1. And y is 1. And so it will be somewhere over here. And z is 0. And then I can do y equals 1. So then we have, move on to the next one. This one would be 2 and 4, and z is 3. Negative 2 and 4, and z is 3. So 2, x is 2, and y is 4. 2 and 4. Sorry. Like about here. And then negative 2. I'm sorry, that one was actually negative 2, 4. And then this is 2 and 4. And so then I can clearly see that this is giving me, there's like a parabola right there. And if my z is changing, okay, I can generate another order pair over here. Yeah, this could still be 1, 1. And maybe z happens to be 3. And this is negative 1 and 1, and z is 3. And I can do the same for all of them, you know. And so it's like it's the same shape, but now everything is shifted up by 3 units. So this is a 0, 0. Then we have a 1, we have a 2, and we have a 3. And right here, it's like I have another one, yes? It's going to be like this. Now, this one, remember that since only one of them is square, it gives you like half of the parabola. It's not the complete parabola, but still it will be okay. Okay. Okay, so now I can have any value of z. I can do another one over here. And we'll do the same. Okay, so now I can complete this. Yes, it will eventually go like this. And so we will have it right here. There's the cylinder. The cylinder is right there. Okay, so there's my cylinder. Okay, so I'm going to make my cylinder all black. Okay, now what I care about is the orientation. Okay, so now I have the cylinder, now I care about the orientation. Okay, let me go ahead and do that in green. In order to do that, the orientation, we're gonna let t be equal to 0. And we're gonna start with that because of this. And so then r of 0, the vector will be 0, 0, 0. So we're gonna plug it in here, remember. Okay, we're gonna let t be equal to 2. And so then that will give me 2, that will give me 4, that will give me 8. Okay, so I am starting here at 0, 0. And then I'm going to go all the way to 2, 4, and 8. 2, 4, and 8. So then this is x is 2, y is 4. So x is 2 is here, y is 4, we're here. We're talking about almost like the same height right here. And then my z is at 8. At 8. Let's just say this is 8 over here. We did say this was 1. This is 2. This is 3. This, let's go ahead and go with 4 and 5 and 6 and 7 and 8. And I'm gonna erase this. But that point will be one of these ones. Yes, it will be like one of these points. Actually, it's the one on the front. It will be one of these ones right here. So that point happens to be that one. Okay, so now my orientation will just go from here. It's going to go this way, yeah? That's it. That will be the orientation. It will be on the surface right here, and that's the orientation for this one. Okay, so hopefully you guys are doing great. I am going to do example 6. One more example. So I think I have given you enough examples of curves. Let's go ahead and do example 6. If you want to, you can pause the video right now and you can try it on your own if you want to first. Okay, here are my components. So x equals 2 cosine t, y equals 4 sine t, and z equals t. Z equals t doesn't help me at all because I have cosine and sine in here. And so not even if I had to replace the t with the z, it would not help me. But since I have cosine and sine, I am thinking how to get rid of those trigonometric names, sine and cosine. Now, I do have three different components. Three different components will give me a surface. Use a ruler. A ruler is best if you want your graph to be a nice graph. For you to see it on my paper, it's a lot better than in here. Okay, so this would be anyway. All right, so instead of me using z, I can divide both sides by 2. So then this is x over 2 equals cosine t, and y over 4 equals to sine t. And I can square both sides. So then this will be x squared over 4 plus, I can square both sides, x squared over 16 equals to cosine squared t plus sine squared t equals 1. So that in reality, I have this. I have two variables. That gives me a cylinder. I have another cylinder right here. My z happens to be free again. So then this will be along the z-axis. Along the z. It might not be exactly on the z-axis like the previous example, but it's going to be in that direction of up and down. Okay, so now I can see the traces. The traces happen to be ellipses. I do have ellipses right here because this is the equation of an ellipse. So x equals plus minus 2 and y equals plus minus 4. And so then that's what I'm going to do, okay? And so then this will give me x is, well, let me go ahead and draw the first one, first of all, before I do some of those order pairs. Okay, so x is 2. And negative 2. And then I have some points in here. And the y is 4. Okay, so then I have my ellipses there. But remember, your z is changing. So you have different heights on the z, okay? But you still have the same ellipse. Your height can change, yes? Your height, let's just say right here, the height is 0. Everything is 0 for the height. But let's just say this is a 1. Let's just say that one's a 2, a 3, a 4, a 5. Let's just say the height happens to be at 6. I will have another one right there. Yes, I will have another of those ellipses. I will have to redraw my X. if you want to draw it nicer and redraw my y. Remember that we did it before this way? And so then I would redraw another one. And so this will be 1, 2, 3, and 4. And then 1, 2, 3, and 4. And then this is 1 and 2. And 1 and 2. And then you can have like another ellipse over here. And so it's kind of hard to draw them. But we can have an infinite number of ellipses along the Z. And so then this will give me my cylinder right here. And so then I have a bunch of ellipses right here. All right, now let's go ahead and move on to the orientation. For the orientation, we're gonna let t be equal to 0. If t is equal to 0, I'm gonna put it into the vector function. So we're gonna put it in here. And so cosine of 0 will be 1. And 1 times 2 is 2. And sine of 0 is 0. And t is 0. So then I get that one, 2, 0, 0. Which happens to be basically the point 2, 0, 0 on your cylinder. Which is this point right here. Then let's go ahead and move on. It says that t is from 0 to 2 pi. So let's go ahead and do pi over 2. Put it inside. So that will be cosine of pi over 2. That will give me 0 times 2 is 0. And then I get sine of pi over 2 is 1. So that will give me a 4. And then, well, z is pi over 2. But I need an approximation to pi over 2. So that will be 0, 4. Pi over 2 will be 1.57. So let's go ahead and go with 1.6. So about 1.6. That will be like another point. This other point happens to also be on the cylinder. So the x is 0, the y is 4, and the height is 1.6. So from here, we're going to go up 1.6. About here. Okay, let's go ahead and move on to t equals pi. And so cosine of pi is -1 times 2, it's -2. Remember that I am plugging it in here. Okay, I'm going to plug in pi. Sine of pi is 0. Then this will be pi. And so then this will be -2, comma 0, 3.14 will be the vector. So x is -2, so we are here. Then y is 0, and then the height is 3.14. So 1, 2, 3, 3.14, like about here. Okay, I don't have any more space. I think I am writing kind of big. Let me go ahead and continue on the side. And I'm going to go with t equals 3 pi over 2. And so I'm going to put it into my vector function. And cosine of 3 pi over 2 is 0. Sine of 3 pi over 2, it's a -1, so that will give me a -4. And then this will be 3 pi over 2. Okay, let's go ahead and convert 3 pi over 2 into a decimal, like about 4.7. Okay, so then that will give me 0. Y is -4. So it's here, then 4.7. Like about here. Okay, let's go ahead and do the last one. Let's do t equals 2 pi. And so when you plug it in, cosine of 2 pi is 1. So that will give me a 2. Sine of 2 pi is 0. And then t will be here, over here, 2 pi. And 2 pi is about 6.3. So then x is 2. Let me go ahead and draw that one in pink. That's 2. And y is 0. And then the height is 6.3. So eventually, remember, I have another ellipse right here. I have a bunch of ellipses. So eventually it's going to hit somewhere on the, every point has to hit on the cylinder. This point right here, it's on the cylinder. This point, it's on the cylinder. This point, it's on the cylinder. Every point is on the cylinder. And it just keeps kind of like going like this inside of the cylinder. It keeps on going like that. It's turning inside. All right, so this is the orientation for this problem. This would be the example that I have given you. Okay, hopefully you will be okay when you're doing this on your own, okay? Let's go ahead and move on to example 7. So now example 7 says, can you find the vector equation and also parametric equations for the line segment that joins the point P1, 1, 3, -2 to the point 2, -1, and 3. Find a vector equation. Find a vector equation. And also, can you find a parametric equation? Well, let's go ahead and find the vector first. We don't have the vector. I'm going to call the vector v. And so then that would be A, B, C. Once I get those components, we can get a vector from P to Q, which I'm going to call B. And so then that would be 2 minus 1, -1 minus 3, 3 minus a -2. And so then I get 1, -4, and 5. And so this would be my vector v. I'm going to choose a point. Okay, so or choose one of the order pairs. I don't care which one. So I'm going to use the first order pair. I'm sorry, order triple. 1, 3, -2. And I am going to set up the parametric equations. Okay, the parametric equations are, it will be x equals, I hope you remember this, x is 0 plus at, y equals y of 0 plus bt, and z equals z of 0 plus ct, where x of 0, y of 0, and z of 0 happens to be the point, and your a, b, and c happens to be your vector numbers. Okay, with that in mind, so now we can replace them. Okay, so I no longer need this. And I no longer need those either. So that would be 1, because that would be, I'm sorry, yeah, that would be the first point, 1. This would be 3. This would be -2, and they're coming from the point. And then the vector numbers are those. This would be 1t. Then this will change into a -4, 4t, and then a 5t. And so then that's it. That would be my answer for the parametric equations. Now, the vector equation, well, I will just put it all together, yeah. R of t, well, this will be 1 plus t, comma, 3 minus 4t, comma, and 5t minus 2, or -2 minus, I'm sorry, -2 plus 5t. And so then that's it. That will be your vector equation. Okay, this will be your vector equation. Now, I gotta also mention a little note. You don't have to do it the way I have it. In the textbook, they also have this other formula for the vector equation. So you can use this other formula if you want to. I am not going to go over this one, but they have this other one. And so feel free to use this one if you want to. I prefer the way I did it. And so in this case, t will be between 0 and 1. The book, once again, the book is using this other formula. Feel free to use it if you want to use it, but you don't have to. This will be the vector equation for us. Okay, for us. All right, so let's go ahead and move on to the the next example. We have example number 8. It says, find the vector function that represents the curve of intersection of the cylinder and the plane. Well, if I compare my example 8 with my example 7, I am already running into some problems. Example 7 had 2 different order pairs, and I was able to find a vector and then use one of those points to generate the parametric equation and the vector equation. But in example 8, I have a cylinder and I have a plane. I have 2 different curves. I don't have a point and I don't have a vector. Okay, so I am missing several things in here. But I had to try to see if it's possible for me to use what has been given to me, for me to be able to express it in a certain way, uh, so I can write down or find a vector function. Okay, and so the cylinder kind of helps me because the cylinder x squared plus y squared equals 1. That helps me because x represents cosine t, parameterized, and y will be equal to sine t parameterized. And so that's actually something that I can use. Okay, with that in mind, now I can use the plane y plus z equals 2 because I can solve for z, and z would be equal to 2 minus y, but y is sine t, so this is 2 minus sine t. And all right, so then that's it, yeah. So then my parametric equations are x is equal to cosine t, y equals sine t, and z equals 2 minus sine t. Now, where t will be between 0 and 2 pi, yeah? Okay, now my vector equation, now we're going to put it all together. You can write it down with i's, j's, and k's, remember that, or you can put it into the vector notation. So I'm going to use i's in this case, so x is cosine t, I, plus y is sine t, j, plus 2 minus sine t, k. One more time, where t is between 0 and 2 pi. One more time, okay? So you can express it in this form, or you can also express it on this other in this other form with this notation if you want to. The reason why I decided to do it with both notations is so you are aware that we can use either one of those notations. Okay, I believe we're completely done with this section. The following exercises are left for you to practice. Go to the tutoring lab and get some help if you need to. We are done with section 13.1. Have a great day, okay? Bye.